So we're here at the IDTechEx show, and hi, so who are you?
I'm Mikkel Kongsfeldt. I'm CEO and co-founder of Radisurf, a Danish startup company in the material science industry, making bonding between dissimilar materials using nanotechnology.
And who are you?
Hi, I'm Espen Dahl, and I am one of Mikkel employees. I'm working mostly with business development, and I'm here today to try to tell the world about Radisurf.
So it says Radisurf. What is a Radisurf?
Radisurf, that's because we are doing radical chemistry on surfaces to change the properties of surfaces to make materials compatible.
So what is this you're showing here?
This is a piece of stainless steel. It's a test sample that's been joined to a piece of acrylic material using our technology. So what we essentially done here is to make a 50 nanometer thin organic coating on the stainless steel part, and then we welded the acrylic onto it to get a really, really strong and tight bonding between the materials.
So you have a tight bond between this and that?
Yeah, exactly.
And what's in between?
In between, there's only a 15 nanometer thin layer of what we call polymer brushes. That is essentially plastic strains that are chemically bonded to the metal part, and they entangle into the plastic part. So what you efficiently create is a direct chemical bond between the metal and the plastic material.
Is this revolutionary? Is very radical? What does it do? What is it for?
It is very radical. It's a completely new way of bonding materials, and it creates a much tighter and stronger bond between the materials. So it enables new possibilities in sealing applications, in sensor applications, where you can get more efficient bonding between your materials.
What are you showing here? Do you have different demos here?
Yeah, we have different demos. This is just to show that if we apply the plastic material in between, we can actually also create a bonding between metal and metal using an interlayer of plastic material and our technology on both sides of the metal. Another application, this is a product that's actually on the market. It's a sensor developed by one of our customers. It's an optical fiber-based sensor where there's a glass fiber in the tip of this, and we bond a small plastic cap to the tip of this sensor to make it function.
So you're enabling a whole bunch of stuff.
Yeah, we are. We're enabling a large range of applications. The sensor application is a really good example. That could not have been done without our technology. We're also making sealings of electronics to make the electronics last longer in more harsh environments, for instance.
Okay. And how about this? What is this here? What do you do with this?
This is a piece of electronics that's overmolded with plastic, and then we efficiently create a better bonding of the plastic to the metal to keep the electronics stable for longer time.
So is this a big deal for the whole electronics industry and everything?
Yeah, it's a big deal because it enables new applications. It enables longer-lasting applications of the electronics.
All right. And what do you talk about here?
Yeah. So this is a description.
So
this is a description of our technology. So what we show here is actually the process of what we're doing. This is a piece of it could be a piece of metal where we show these polymer strands that we grow. They're chemically bonded to the surface, and they actually grow up from the surface to create a really high density of these chemical bonds down to the surface. And then they act as kind of a nano velcro to entangle into the plastic materials during bonding, which efficiently creates this direct bonding between the materials.
Is that what the lizards do when they walk on the ceiling?
It's not exactly what they do when they walk on the ceiling. This is on another scale, and that's why what we create is a permanent bonding. What they create is not a permanent bond because they have the strands on another scale, a larger scale actually.
Humans have not been able to copy that yet, right?
No, I don't think so. No.
But so what you're doing, is that radically revolutionary? Nobody else is doing this?
So what we're doing here, building these polymer brushes on surfaces, that has actually been a well-known technology for 30 years to do that, but only in controlled environments and laboratories. What we're doing is taking it out of laboratory, and we're able to scale it up to an industrial scale, and I believe we are the only ones in the world who can do that.
And what are you talking about here?
What we talk about here is our project model of how we work with our customers. In this case, we approach every customer's problem as a unique problem, and we work with them to solve their needs. And then we work through a phase of scale up and up to full scale production, where we help the customers all the way until they produce the components in line in their productions, and we only deliver the chemicals for their needs.
And when you talk about here?
Up here we talk about the different materials we can work with. So these are examples of some of the materials that we work with. So the different types of substrates, metal, alloys, carbon materials, glass, and the different polymers that we can actually bond to.
Is it a lot?
I think this is a lot. It's not an exhaustive list. We have other polymers that we're working on. We're constantly expanding our portfolio of materials that we can work with.
So why do you need this plastic kind of thing, right? Polymer is a plastic or what?
Yeah, it's a
so
plastic.
So why do you need the plastic to make things bond? Can you not just do some these brushes on something else? Is it a secret?
No, it's the brushes are essentially also plastic chains. So that's what's really unique here, is that we actually grow plastic chains from a metal surface, and that enables the bonding to the metal surface.
And how do you make this in industrial scale? How do you make it in big scale?
The big point here is that traditionally to do these polymerization, growing these polymer brushes, you need inert atmosphere and really, really long time. What we've done is to create another way of making catalysts for this that enable us to do it in open atmosphere and on much shorter time scale. So we're down to minutes, whereas the traditional way is several hours.
So what does this mean for the future of like the world? Are we going to have totally different kind of devices where they're let's say if this is going to be a phone or something, right? You'll have plastics and metals and everything somehow connected?
Yeah, so what it really means is that it enables new designs, new applications. It enables new material combinations to be used in products. So essentially it gives the designers who are designing new products, the engineers who design new products, it gives them a whole new range of opportunities and design freedoms.